a spring like this is going to be our medium. When the spring is not disturbed, I call that being in the equilibrium position. The equilibrium position means that there's no disturbance in the medium. Line it all up right on that line. Now I'm going to disturb the medium. I'm going to give it a little bit of a disturbance. And what you notice is that disturbance travels or propagates. We say the wave propagates from one end to the other. 2-foot disturbance. And notice that that disturbance started off here being 2 feet, like that. We call that the amplitude. That is a 2-foot amplitude disturbance, or the wave had a 2-foot amplitude, like that. The height or the tallness of the disturbance is called the amplitude of the wave. The amplitude of the wave is a measure of how far does the wave travel, how far does the medium travel away from its equilibrium position. And in this case, that was 2 feet. I want you to focus on 2 things right now. I want you to focus on how the spring moves, and I want you to focus on how the wave propagates. So we've got the movement of the spring and the propagation of the wave. So go ahead and do that. What you should be seeing here is that the spring itself vibrates back and forth like this. So the medium is vibrating this direction. But the wave, as you saw, propagated from here down to there. So the wave propagation is in this direction. So the medium vibration is perpendicular to the wave propagation, and I call that a transverse wave. Your job is to stand right here and count the number of times the wave crest goes by you in 1 second. Just 1 second. Here we go. Yes. Okay, get ready for your count. Count how many wave crests happen in 1 second. 1. One wave crest went by her in 1 second. We call that a frequency of 1 peak per second. 1 peak per second. And that's called a frequency. 1 wave crest went by here in 1 second, and the frequency is 1 per second. Okay, now count again. Same thing, same job. Get ready. Now how many went by?
2.
That's a frequency of 2, because 2 of the wave crests went by her in 1 second. What happened? Nothing changed. The size didn't change. What changed was how many crests went by her. I'm going to try it again. Here we go. Now, okay. Here we go. Now what happened was there was 3 wave crests that came by her in 1 second. And so the frequency is the number of wave crests that go by her in 1 second. If it's 3, that means 3 wave crests came by in a second. If it's 1, it means 1. That's what frequency is. What we did today that was new was I defined for you frequency. And frequency I defined as the number of crests per second that pass by a location. So it's the number of crests per second that pass by a location. If I said that the frequency was equal to 30 peaks per second, that would mean that 30 of those wave peaks passed by a spot in 1 second. The most common way we write that is 30 per second. And the way I write that is, and the way I say that is 30 per second. The most common way that it's written, or another common way, is 30 times s to the negative 1. Because s to the negative 1 is the same as 1 over s. And the most common way this is written in your book is 30 hertz. All right? What the heck is that? Well, note to self, a hertz, which is really short for H-E-R-T-Z, is really the same thing as 1 over a second. Hertz was a physicist from the 19th century, and he did a lot of work in this area, and so they honor him by naming the unit for frequency, which is 1 over a second. They just name it a hertz. So if I say that a wave has a frequency of 30 hertz, what that means is that 30 peaks per second passed by my spot. If I said it had 100 hertz, that would mean 100 peaks per second passed by my spot. All right. I heard a lot of people saying it right. I'm going to draw a little picture here, because a picture is worth more than I can say, more than you want to hear. And the wavelength is the distance between these two peaks. The distance between two peaks. Now I've got a note to self over here. This funny little upside down Y is actually a Greek letter. It's a Greek letter called lambda. And the Greek letter lambda is the letter that we use to represent wavelength. So when you see that symbol, that upside down Y, it's a Greek letter lambda, and what it means is the distance between the peaks of those two waves. Well, the units of lambda are meters because it's a distance, and we measure distance in meters. So now, I've defined two things for you, frequency and wavelength. They're not the same thing, but they're related. And so now, I'm about to give you the main point, the big idea, the reason that these last two lectures have happened and the demonstration, so that we could define the next thing. So this next thing is the big idea. So get ready for it. There's a relationship between frequency and wavelength, and that relationship is given by this equation, where V stands for what we call the wave speed. F stands for the frequency, and lambda stands for the wavelength. What this equation says is that the wave speed is equal to the frequency times the wavelength. Wave speed is, it tells me how fast the wave travels. When you saw that wave travel down the spring, you could see that it moved from one point to another. When it moves from one point to another, it has a speed. That's what the wave speed is. The frequency tells how many peaks passed by in 1 second. And the wavelength tells the distance between peaks. This equation has a name. It's called the wave speed equation. Duh, because it describes the speed of the wave. And it's equal to the frequency times the wavelength. This is the big idea I want you to know. So right now, here's what I want you to do. I want you to spend the next 20 seconds writing a brief paragraph. 3 to 5 sentences is all you need. Maybe 5 or 7. To summarize what the big idea is here. Summarize that in your notebook. Just summarize it. The main idea is that the wave speed, that is to say the speed with which a wave propagates through a medium, is equal to the frequency of the waves in that medium multiplied times the wavelength of the waves. In other words, the wave speed is related to both the frequency and the wavelength. Or another way to say it is, the product of the frequency and the wavelength is the wave speed units. Here's the wave speed equation. What are the units? Well, what are the units of frequency?
Hertz.
Hertz, or another way to write it is?
HD.
1 over seconds, right? I could say hertz, you're right. But what does hertz mean? It means 1 over second, doesn't it? Multiply it times, what are the units of lambda? Meters. When I multiply 1 over second times meters, what do I get? 340 meters per second is roughly the speed of sound in air. For those of you that don't know, a piano has a bunch of keys on it, and they play different frequencies of music. You've heard the high end, ding, 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 and the low end, dong, dong, dong. So it goes from high to low. If you played one of the lowest keys on the piano, you would be playing a key that creates a frequency of 24 hertz, roughly 24 hertz. I'd like to find what the wavelength is of that frequency or that chord on the piano. Well, I'm going to draw a picture of this, a simple picture, and my simple picture looks like this. I've got a wavelength here that's unknown. But what I know is that the frequency is equal to 24 hertz, and that this wave is traveling with a velocity that's equal to 340 meters per second. So that wave is traveling at a certain velocity. And I have to find lambda. Well, I'm going to start with my wave speed equation, and there it is. I'm going to do one step of algebra to solve for lambda in that equation. Now I'm going to say that lambda is equal to the velocity over the frequency, and in my case, that's 340 meters per second divided by 24 1/2, that's a hertz. And that comes out to be approximately, lambda is approximately 14. And now I'm going to work on my units. My units are meters over seconds divided by 1/2. That's a compound fraction. I'm going to invert and multiply. And when I invert and multiply, the seconds cancel, and I end up with meters. And those are the units that I expect for a wavelength, because a wavelength is measured in meters. What does that even mean? It means that if I play the low chord on a piano, that chord will create a sound wave with a wavelength. I can't see the wave, I can hear it, but I can't see it. But if I could see it, the wavelength would reach 14, this is 1 meter, so it'd reach 14 of these, out the door, down the hall, almost halfway to the corner. That's how long the wave would be. And so what I just calculated was the wavelength of a 24 hertz sound wave traveling through air.